Okay, so that's basically brings us to the end of our discussions. We'll take questions and then I will summarize what we have done. Okay, the first question is it possible for polytropic process to occur naturally? And the answer is yes. In the sense that if you see, say, air flowing through a building, or at some point there is a contraction and air goes through it, the velocity goes up. And even though we assume temperature to be constant, we can, the thermodynamics of that we can approximate that as PV to the power n equal to constant. If you mean that naturally that you leave something to itself and it will do it, that's also possible. You take a, say, a shock absorber and you compress it and let it go. As it comes out by itself, it could follow that sort of a thing, especially a gas-filled shock absorber. That's what it will do. So it is possible that because those processes are irreversible, that's why it is not PV to the power k equal to constant. The irreversibility will make it n, even if that device was adiabatic. Okay, so if it is reversible and adiabatic, then the exponent is k. But if it is irreversible, internal irreversibility is in the device and adiabatic, then this will be n, and typically this will be slightly less than k. If you are cooling it, then of course n will come down even more, and so all things like engines and compressors and things like that, n is less than k, which if you do a complete analysis will show you is not a very good thing, because that's not the best efficiency, best way to do that compression. So people try to make things that we would like to make it as adiabatic as possible. And a lot of work has gone on in saying, can I make an internal combustion engine where the cylinder piston arrangement is adiabatic? Right now it is not. When you look at a motorcycle engine, it has got fins on it, so whatever heat was there generated by the burning of the fuel, some of that was conducted to the atmosphere through the piston and the fins, and the rest of it, you got some work out of it. So by burning fuel, you lost some energy to the atmosphere, and that was not the best thing to do. So I make it adiabatic by putting a lot of insulation on it, fine, but then the material will run much hotter. It will get very hot, and materials like aluminum or aluminum alloys may not be able to withstand that type of a temperature. They may lose their strength, their docking, their wear and tear may happen, the lubricating oils may get burnt up or destroyed, and so the engine may not be very a long-lasting engine. But that is definitely a thermodynamic basis and the reason why you would like to make such a process adiabatic. Okay, could you please explain the importance of Gibbs energy? Okay, I have deliberately not gone too much into detail on that, but Gibbs energy basically tells you that, for instance, in a chemical reaction, we know that we get so much heat out of it. The question is, if instead of that chemical reaction happening, and instead of taking it out as heat, what if is it possible that what the work I can get out of it? And that is what Gibbs free energy tells us, that is the maximum work that we can get from a particular process. In the case of non-reacting systems, it has got a slightly different connotation, but it essentially is still saying that it is the maximum work that you can get without say interaction with the surroundings. That's very roughly what Gibbs free energy is about. Okay, so what we have done in this course, we have 3 modules so far, and now we have covered all the knowledge that we want to solve a problem. We have everything. Whichever problem, whatever way it is, now that is not an issue for us. We know how to do a first cut analysis of all these type of problems. In the first one, we said we have to worry about concepts and definitions. In the second, we said what are the laws. And what we learned was universally true. There was no ifs and buts. It did not depend on the application. It did not depend on the examples. And now we looked at to do calculations of changes in properties. We have learned how we can compute and calculate the properties of a pure substance. So all of these together now give us the confidence that we can completely solve a problem and answer various questions. So let's take a couple of examples. We say that we have a cylinder piston arrangement in which the piston moves from this position to this position. These are stage 1 and stage 2. There is some material, some substance in it. And during this process, certain amount of heat was given to it. And we want to calculate what is the work done by the device. So we know now, we start off the way we did in the beginning, that we identify the system boundary is what we draw first, and say whether it is an open system or a closed system. And we say this is a closed system, so the way the equations will be that mass of what is there inside this is constant. That means mass in state 1 is equal to mass in state 2, conservation of mass. And the first law tells us that Q12 is equal to W12 plus E2 minus E1. And then we make some assumptions of delta KE, delta PE being 0. And that comes that Q12 is equal to W12 plus U2 minus U1. So we need to calculate various things, and we then write down what is it that is given in the problem. Say state 1 is fully defined, that P1 is given and V1 is given, and say mass could be given, which means that specific volume at the beginning is known. And we say state 1, I have two independent properties, I can get enthalpy, entropy, everything else that I want. And now it depends what's with state 2. We know that if it went up there, the mass was the same, M1 equal to M2, the volume increased by doubled or tripled or quadrupled, whatever, specific volume change we know, but say we don't know what the final pressure is. If we are given the final pressure, P2, then we say that, well, now I know both things, or say T2, and we know that state 2 is defined. We can get U1, U2, and if heat transfer during the process was known, the work for this process can be calculated. And what one does then is that at this point, what we had not done so far in our problem solving was say, what is the substance? Having learned the properties of the pure substance, we now have to make a decision. Should I assume this to be a vapor and go to the tables and charts, or should I assume this to be an ideal gas and use PV equal to R? This is an important decision we have to make. And for that, we need to look at the problem and say, well, what is it that is given here? This could be superheated vapor. In which case, your first idea should be that, look, I must treat it as a vapor. Let me not assume a priori that this is a gas. At the end, I will check again if it is a gas, that's good enough. Or if I don't have enough other information, I may assume this to be a gas and find out what. So this is the next decision we make, that if I need to get the properties, do I have to have a vapor or an ideal gas? And from there we get the equation of state, and from here we go to the charts and get property data from there. And then we put it in this, go back, calculate what is U. If it was from the vapor charts, this U will be computed by looking values from the tables. If it is an ideal gas, we would put U2 minus U1 as CV0 T2 minus T1. Or from the charts, we directly read out the two values, and if values of U are not given, you would definitely have values of H which would have been given. So we can get H2 and H1 from the charts. P1, V1, P2, V2 are known, and from there we can get U2 and U1 and substitute in this equation. And then we do the remaining calculation. So this is the additional thing we have put, and in doing that, we are now actually putting numbers on all of these. And that is where we are getting quantitative and getting numbers. So we did not do that at the end of module 2. We just said that I knew the property and we gave some arbitrary symbol to that property. Now what we will do is go back and put numbers on that property, put a title or a name on the substance and solve those problems. That's what we will do now. We can also use these properties to do various checks and balances and say, take an open system. And so somebody says that I have made an adiabatic plus reversible turbine that can expand from P1 T1 state to P2 T2 state and produce this much amount of work, or this, or W. And the first question we ask, is such a machine possible? So we go back and say, look, this is a turbine that we are talking of. So that's this picture. There's the substance going in, the substance coming out, and there's some work coming out. There could be some heat, but if it is adiabatic, this Q dot CV, this is equal to 0. And all we are left is W dot CV. And now, say, well, the problem would tell you that gas expands in a turbine, and that automatically tells you that word gas, that you can take it to be an ideal gas. Or if we say it is steam expands in a turbine, then by default, we presume it is not an ideal gas. So that question will get answered, vapor or ideal gas. And then we draw the process on a property chart and say, well, this is state 1, they have given this, and this is a state 2, or maybe state 2 could be there, or state 2 could be there. We don't know. And if we plot it, we can very quickly see one thing, that if on this plot, this exit state, so this is the isentropic case. If the final state is to the right of this, the turbine is possible. If the final state is to the left of this and it is adiabatic, the turbine is not possible. So what we have done is we went and said, well, I will calculate S1, we will calculate S2 and ask, is S2 greater than S1 or equal to S1? If yes, turbine is possible. No, turbine is not possible. The work that is claimed, it may be right by the first law analysis that this work would have been m dot, or m dot is 1, H2 minus H1. And this came from a series of assumptions that we have done. So this may be true. It is getting that much work. But if S2 is not greater than S1, then even though it satisfies the first law, it says, no, this is not possible. You cannot make such a thing. We'll take one more example and then we'll stop. We will look at analysis of a cycle. And what we have learned now is that a Carnot cycle has 2 isothermal heat transfer and 2 adiabatic reversible work producing. And now we say what constitutes in the real world for a given substance on this TS diagram, where is a Carnot cycle? So what we do is we just say that here is the saturation dome, and we know from what we saw yesterday on the TS diagram that even at very high pressures, this line goes very close to it and it goes like that. That means to the left of this, states are not possible. All the states are to the right of this. And if this is what the Carnot cycle is, what it tells us that any square or a rectangle is a Carnot cycle. If it goes this way, it's a work producing cycle. If it goes the opposite side, it's a heat pump or a refrigerator. So it has 4 states, 1, 2, 3, 4. And we want to know what is the work done per cycle. So we need to know what is the different cyclic integral of heat or the cyclic integral of work, and that will be the answer. So cycle could be there on this property diagram. Now we are putting numbers. Nothing stops us from saying that I have a Carnot cycle sitting over there. Perfectly fine. Somebody says I'll make a Carnot cycle like this. Theoretically, absolutely no problem. Practically, we start seeing some problems. That it is now gone into the wet region, and as work producing or work consuming devices go, so W type devices, turbines, compressors or anything, there is one fundamental principle of engineering that this will either be a liquid or it will be completely a vapor or ideal gas. It will not be a wet state. There are serious engineering issues with this. Why? If you want to make like this or like this, it's a very, very difficult task from an engineering perspective. Thermodynamics says perfectly fine. So you can make a Carnot cycle there. One can even say I'll make a Carnot cycle there or a Carnot cycle over there. But somebody says, well, I'll make a Carnot cycle like this. Theoretically, all of them are possible. The efficiencies, we can see what they are. Practically, if we start putting numbers on it after selecting the material, so we select the working substance and start looking at what numbers start coming out for specific volume, enthalpy changes and things like that, then we will see that there's a big problem. Something is possible, something is not possible. A Carnot cycle far away from this dome, like this one that I have drawn, this is completely an ideal gas thing, quite nice and easy to look at. A cycle which could be like this would also be a Carnot cycle, somewhat possible, but still it has got problems with it. But this will be a vapor thing, this will be only an ideal gas cycle. So when we have 4 such states, how do we do the cycle analysis? And for that we need 2 independent properties at every point. And let's see what happens in this case. What I do is make a little matrix. On this side, I put the state numbers 1, 2, 3, 4, and this side properties P, T, V, H, and S. So how many properties do I need to know to define the Carnot cycle? One is of course T1 and say T4. So I say I have specified this and I have specified T4. And then say other pressure at and the other 2 states, I need something more, and let's take that say that we know the pressure in both cases. Question is, do I have enough information to complete this table, which means that do I have 2 independent properties at every state? And so let's quickly go through this. Say if state 4 is fully defined, then I can compute V, H, and S. And I know from this that S4 is equal to S1. So if this is known, then this is known. The 2 are the same. And then we look at this thing and you say, if I know T1, do I know T2? And the answer is yes, this is the same T2. And from here we know that T3 is same as this, so this T is also known. So now we have got 2 independent, one property at each of these states. And we tell you, what do I know about 2 and 3? The entropy is the same. So if I get entropy at any one of these, which is, say, if I know one of the properties, then this is there, and then this comes out. And like that, we can complete this table and say that S1 is equal to S4. So at this is entropy we have already taken. S2 equal to S3, T4 equal to T3, and T2 equal to T1. And with doing that, you can see that if we get two independent properties at any point, the rest of the entries in this table we can very quickly complete, whether it is a vapor or whether it is an ideal gas. Once we have done that, and maybe we may not need all the properties at all points, specific volume may not even be needed, then we can go back and calculate all the other things which the law requires us to do, that work is equal to the cyclic integral of heat is this property minus that property minus this property, like that. And we can calculate all of that. So this is one way we can tackle cycles by making a matrix and asking ourselves, well, in the problem, not necessarily in the numbers but in the words, do I have enough information that I can calculate two properties at every state? If the answer is yes, then it is possible to solve the problem. Then we go ahead and solve it. Okay, what is the question between nozzle and diffuser? Okay, so I'll take that up. Okay, so there are two devices, a nozzle and a diffuser. Now this is a device which accelerates a flow. That means in the direction of flow, the velocity increases, pressure decreases. The diffuser is exactly the opposite. It decelerates the flow. That means in the direction of flow, velocity will decrease and pressure will increase. So if you look at, say, air going through a passage like this, here the pressure is P1, T1, and it goes through this and comes out at a higher velocity. The pressure here has become P2, T2. The velocity here, V2, is much greater, or say greater than 1, and P1 is less than P2. So this is a nozzle. With the one little caution, that those of you who have gone into compressible flow study, you realize that this is true if everywhere in this, the Mach number is less than 1. It is a subsonic flow. Now if you just reverse everything, we get a diffuser that you send in here at P1, T1 and some velocity V1, and what you get here is P2, which is greater than P1, V2 is less than V1. And where do you see these type of things? If you recall the rocket that I showed you, PSLV being launched, at the bottom of the rocket, you could have seen a structure like this, from which there were gases coming out. This is a diffuser. So we produced high temperature gas, then we accelerated it to make it high velocity by dropping the temperature, and then we got it out here so that the pressure increases and there is pressure acting on this which pushes the rocket up. So diffusers are required in those rockets. Like before, this is also the case here, that this will happen if the flow everywhere is subsonic. And the reason for putting this is that if the flow were the other extent, that Mach number is greater than 1, which is the supersonic flow, then exactly the opposite will happen in this passage and opposite will happen in this passage. This will decelerate the flow, this will accelerate the flow. Okay, but that's for a different type and a different course. Right now we are not going into that, so but just for completion of the description of what's a nozzle and diffuser, I have shown this. In both cases, if there is no other dissipation and there is no heat transfer, ideally both would be isentropic, S equal to constant. If there were irreversibilities, exit entropy will be more than inlet entropy, and on the property diagram, say TS diagram, the nozzle will look like this, ideal nozzle, and the same pressure, a real nozzle will do this. And a diffuser, from here, in the ideal diffuser, it will go over there. The real diffuser, this will go there, and this will be the exit state. Okay, so we will conclude at that point that we have now got all the theory and the property and the laws cleared up, we have already attempted a certain systematic way of solving problems, and in the last module we will come with applications and we will solve some problems during the lectures. If you want some particular problems to be addressed, please post it on the forum. I will address that in the last module. So with that we stop, and thank you.